So this is going to be a differential calculus study session using the IBHL Applications Interpretations Hodder Education textbook. I don't know by what author and like what year published, but it's going to be the mixed practice section. And unfortunately, because my TI Inspire is not fully charged today, we're going to have to do a TI-84 Centric, but there are similarities between graphing calculators, which I'll go and elaborate. And we'll just see how long we go at solving these problems. I can't guarantee that the answer to these problems will be correct. If they are incorrect, especially since applications interpretations is very number-centric, I will go and look at the back of the book and then possibly write down in the comments section what the actual answers are, if there are any discrepancies, and possibly where I went wrong. But anyhow, with that being settled, I have to go and erase this to make room. And let's get to it right away. You have the curve y equals x squared plus bx. Screw it, I'll just go and write it in cursive. Bx plus c which has a minimum value at, what's the number? 2, 3. So find the value of b and c. Okay, at the end of the day, this is going to boil down into a systems of linear equations problem. And since you have two variables here, you'll need two equations. Two variables, two equations, EQ. That's the checkbook that you'll need. Okay, so how do we go and find the fact that it's a minimum in this case? Well, we have to go and find what the critical point of this thing is, and then we have to classify it as a minimum. Simple thing, that's dy dx equals 0, turning point. And then to make it be a minimum, the second derivative along that interval must be positive. Okay, that's what we're going to do. Let's go and apply for this function now. Dy dx equals 2x plus b. I do the power rule to the x squared, the 2 comes down, minus 1, get 2x here, bx, that's a linear coefficient, sorry, a linear term, take derivative of that, you only get the coefficient left. Derivative of constant, 0, gets destroyed, gets cancelled completely. So you just have this, and then you set it equal to 0. Okay, and next one is, if I'm B and C. Okay, so then we solve for b, which is then b becomes minus 2x, and we're given that the x coordinate is 2, so that's the same as minus 2 times 2, which is minus 4. Oh wait, actually never mind. Doing the second derivative is pointless, because if I do the second derivative, I get d squared dy xt squared, which equals 2. It's independent of x, so this is always going to be positive. X is positive along any real interval for the real numbers. So this is good enough. B equals -4. Sorry about that. Then in this case, all we can do in order to get b and c as both variables is to go and plug these two coordinates into this equation over here. So then we get 3 equals 2 squared plus b times 2 plus c. And then there you have an equation in terms of b and c. Oh, actually this is even easier. Okay, I guess this is really nice that it's equal to 0. So you don't need to even use like linsolve, like I thought you have to do. So 3 equals 4 plus 2b plus c. And then we have what b is. B is negative 4. So then that means 3 equals 4 plus 2 times negative 4 plus c. That's 4 minus 8 plus c. 3. So that's 3 minus 4 plus 8 equals c. Go into your calculator and stuff because I like suck at mental arithmetic. 3 minus 4. 3 minus 4 plus 8. That's 7. That's c equals 7. So the answer is c equals 7 and b equals negative 4. That's the minimum value at 2, 3 for that constraint. Okay, hope that's good. We'll move on now. Find the derivative of e to the x squared. This is almost the Gaussian PDF distribution function, but not quite, because it's an x squared instead of a negative x squared. Alright, so we're going to have to take the derivative of an e to the x clone. So one good thing to know is that if you do like the derivative of e to the x is a meme, it's invincible. You just get a copy of itself back, just based on the definition of its limit. So that's e to the x. And then this is a composite function. Function inside a function. I'm probably going to get the mapping wrong. It's like x to x squared and then to e to the x in that order. Could be wrong, but that's not really relevant for solving this problem. It's really just taking the derivative of this thing. Now let's see. If I do derivative of this, when taking derivative of any natural exponential function, you're just going to get a copy of the exact function back. So you get e to the x squared. However, you need to take the derivative of the inside expression, which in this case is the x squared, and then multiply it outside by the chain rule. So what's the derivative of x squared? That you just apply the power rule, go down 1 degree, so that's 2x. Boom, done, nice and simple. Okay? Yeah, so that's the answer. Find the second derivative of y equals 1 over x plus 2. One over x plus 2? Yeah, 1 over x plus 2. Here, I do not advise, in my opinion, using the quotient rule. I advise first rewriting this as a composite function, namely x plus 2 raised to the power of negative 1, and then do the chain rule on that. So then we do it one time. I'm going to be like, no. I should be consistent with the notation. I would stick to the Leibniz notation, or is it Newtonian notation? I don't care whose notation it is. So take the derivative of the outside expression. This is stuffed to the negative 1. Negative 1 comes down. Minus 1, that's negative 2. So you have negative 1 times stuff, x plus 2, raised to the negative 1 minus 1, if you want, so that's 2. And then take the derivative of the inside expression. That's a constant, that's 0, that's x, that's just 1. Done. Negative x plus 2, negative 2. Now I have to take the derivative again to get the second derivative. So then that's like negative 1, bring a negative 2 down this time, then x plus 2, and then minus 2 minus 1, which is minus 3, which becomes 2x plus 2, negative 3, and since we can bar, since this is the final result, we can put this in a nice form as 2 over x plus 2 quantity cubed. Done. Done, so to speak. Okay, this one is going to be interesting. differentiate sine x over x. If you're interested why this particular function is important, it's kind of one of those weird pathological functions where weird stuff, pathology means weird stuff happens. And I believe you also needed to use with the squeeze theorem to go and conclude that the limit sine of x over x equals 1. Yes, as x goes to 0. Yeah, so that's how this is important. And that's critical for deriving the derivative formula for sine of x, or cosine of x. So we want to differentiate this. Since you have a trigonometric function and then you have a linear function here, you can simplify those, combine those together. You just have to use quotient rule. Or you could do product rule with the x over here being brought to the top as x to the negative 1. In fact, I prefer doing it that way. So f of x equals... I'm very anti-chain rule biased, if you don't know already. So then f prime of x... Okay, to differentiate the thing... Okay, you know what? I'm going to list the little steps here. We break it up into two component factor functions. So this is u, this is x to the negative 1, this is v, this is sine of x. Just going to do du to be lazy. Differentiate that, you bring the negative 1 down, minus 1 on the top increment, that's negative x to the minus 2. Now if I do dv, okay, if you do derivative of trigonometric functions, periodic trigonometric functions, here is this nice trick. Given that you parameterize the trigonometric functions to be a unit circle and polar coordinates, so say like this is x equals cosine theta, right? That's just a unit circle parameterization, and y equals sine theta. This is x equals minus cosine theta, and then this is y equals minus sine of theta. When you're differentiating a trigonometric function, you will always be rotating clockwise. So going from this to there, this to here, this to there, and this to there. So the derivative of sine of x is just going to be cosine of x. And then you leave one constant, you leave one part of the function alone, you punch differentiate the other function, then you set this function constant, and then you differentiate this other guy, which could be interpreted as cross-multiplying these guys and then adding them up together. So this is going to give us x to the negative 1 cosine of x minus x to the negative 2 times sine of x. And then you can write that as cosine, if you want, as cosine of x over x minus sine x over x squared. And if you want to combine them together in a single fraction, you can just like multiply this by a sneaky one identity pair, which is like x over x, if you want. I'm not going to bother doing this since we're AI and we just care about getting the final result, so that's done in my book. Find f prime of x if f of x equals x natural logarithm of x. You have a polynomial function, really simple polynomial function, and a transcendental function, which is a logarithmic function. We're going to be using product rule. I'm going to be using product rule. F prime of x. Actually, let me break down. Sorry, I'm rushing. Let me break down the steps nice and easy. U equals x. V equals, sorry, not V, du equals 1. V equals natural logarithm of x. dv dx, I'd just be lazy or stuff, that's just like 1 over x. Cross multiply these guys together and then add them up. Almost kind of like a dot product kind of thing, almost. So then that's x times 1 over x plus natural logarithm of x times 1, which is 1 plus natural logarithm of x. Is that right? That doesn't sound right to me. Let me look at it again. No, that's right, that's right. Okay, fine. I guess I was confusing it with like the integral or the series related to this. Something. Yeah, no, we're good. Okay, yep, that's done. Moving on. Okay, I'm picking up this book now. Find the gradient to the tangent of the curve y equals gradient to y equals square root of x minus 1 at x equals 5. So the thing we want to do is, we hate radical notation now, we're going to turn this into fractional exponent notation, so that's x minus 1 to the 1/2. And I want to find a gradient, we just like find the derivative expression and then plug in this input value here. So then this y prime is going to be 1/2 x minus 1. 1/2 minus 1, so that's negative 1/2. And then we input in our initial condition value, y prime of 5 equals 1/2. 5 minus 1, negative 1/2. I can do this quick, so that's 2 over square root of 4, which is then 1 over 2 times 2 equals 1 over 4. Easy. Done. And then, let's see, find the equation of the tangent. Find equation of the tangent. To curve y equals ln of x at x equals 1. Oh boy. Okay, so first you need one thing, because tangent equation is basically making a linear function out of the slope you get once you found that gradient on the derivative function. So first we need to find a point, or that's one where you can do. So you do y of 1 equals natural logarithm of 1. Natural logarithm of 1 is 0. I'm not going to explain that. That's 0, 1 is a point. Now we need to find the gradient at x equals 1. So dy dx equals 1 over x, and we want to plug it at x equals 1. That's 1 over 1, so that's 1. So this is essentially the slope. So I would just use point slope form to cheat. So like y minus y naught equals y prime times x minus x naught. And this is at a point, this is at x equals 1. So then we have this to be 1, right? I'm getting overfilled here. Yeah, that's 1. And then you have x minus, so this is the x naught. This corresponds to x naught, y naught here. This is x minus 0. And then this is y minus 1. So then, if you want, you can simplify that, but honestly, point slope form is the standard form, so I'm going to be lazy and just leave it like this. Because you're IB students and you're a test prep exam, so you're under a time limit. So you just gotta go fast, unfortunately. Okay, similar to that, except we're finding the equation of a normal line, but for a different function. Normal function is almost, sorry, not normal function. Normal line is almost the same, except once you find that particular gradient, you do the negative reciprocal of it to find the slope of the perpendicular line. Because that's what all the gradient is, it's just slope. So normal line, gonna be lazy here, normal line to y equals e to the 2x at x equals 0. Y prime, e to the 2x is a composite function, e to stuff. So then you get a copy of e to the 2x, but then you need to multiply by the derivative of the inside expression, which is 2x, that gives you 2. Y prime, you plug in the 0 in here, that's 2e 2 times 0. 2 times 0 is 0, and e to the power of anything 0, or any base to the power of 0 is 1. So 2 times 1 equals 2. And now we need the point. I'm getting tired. I am so tired. Okay. 1 here. Okay. So then the point is 0, 1. And then this is 2. So then we have y minus 1 equals 2 times x minus 0. There, I made a mistake. I forgot to take, Yeah, I'm sorry for that. I made a mistake, big fool of myself. I forgot to go and get the slope and take the negative reciprocal of it. But I can still use this, right? Just trying to think. Yeah, it shouldn't matter, it's like on the same curve. Okay, so we'll use this point, we'll use the 0, 1. Yeah, I'll do it again later just so I get it in order. So then this is the gradient. Hence the normal slope equals negative 1 over y prime 0, which is negative 1 over 2. And then once again we have y of 0 equals e to the 2, 0, which is just e to the 0, that's 1. So we get 0, 1. So then the normal equation is y minus 1 equals negative 1/2 x minus 0. There, that's the point. And now I didn't screw up. Okay, we're good. Okay, this is going to be a related race problem because we're having geometry now. And thankfully not angle geometry, screw angles. A little bit of Wahlberger in me with that. So you have a cube. S. The side of a cube is increasing at a rate of 0.6 centimeters per second. That means we're differentiating with respect to time. So ddt. Here, Leibniz notation is superior to Newtonian or Lagrange notation, for that matter. So the side of a cube, and it could be any side, we're just given that ds dt equals, and it's increasing, that means it's positive, plus 0.6 centimeters per second. So that's increasing at rate of find the rate increase of the volume. read the thing. Find the rate increase of the volume when side length, so like when S equals, what's the number? 12 centimeters. Okay, so this rate increase of volume is essentially going to be dV dt. Okay, well here you need to go and like pull out your formula booklet for geometry, or you memorize it. In that manner, I would recommend just like refer to the formula booklet you have for geometry. No one remembers this stuff. So V volume equals length times width times height, so that's S times S times S, S, that's S cubed. And if I were to do dV dt, oh, here's the thing which I failed. Should have gone a bit slower here. S changes with respect to time. So this is actually yet another composite function. The volume is defined in terms of the S, so there's a composition of the length of the cube, side length of the cube, but it's being composed with the time in which the rate of the side changes as well. So this I should really define as V of S of t or if you want, you could do like V this S of t, lost, whatever. And that's the same as S times S times S, which is essentially going to be S of t cubed in that case. So if I were to do dV dt, which depends on S, dear God, please bear with me. I'm just so the notation will look ugly. You could just write as dV dt if you want for our purposes. But for this problem, this dV dt is the same thing as V prime of S of t V prime of S of t, and I'm mixing notations now, that's a little bit nasty. And then ds dt, let's see if I can write this purely in terms of Leibniz notation. That's dV dt of S of t, yeah. Okay. Give me a second. Give me a second. Time 20 minutes, 12 seconds. Okay, let's get going. Sorry, I'm experiencing fatigue now. Okay, let me think of it this way. D dt d dt of this mess yeah, isn't it just like dV dt? Oh yeah, you just multiply together. I'm dumb, sorry. Yeah, because essentially, if you do this, you take the derivative of this with respect to s first, so that's dV over ds. Okay, I'm stupid. Okay, or rather, I haven't really rigorously worked with this notation or stuff. I should go and put in the skip line when I have the chance in here. Like, this is just a waste of time fuss about notation. Sorry about that. Yeah. So then that's it. dV ds times dV dt equals dV dt. So then dV dt in this example is free s of t squared, and then you multiply by ds dt in this case. And we're given ds dt, that's 0.6, but we need to find when s equals 12, when we increase when s equals 12. Yeah, it doesn't specify, it doesn't have to, you could specify like what time it is, and then, oh wait, we don't have like a cube function. Never mind, it has to be a constant. Okay. But if s were non-constant, then this is how you do it. So because they're really nice to us, because it's an easy problem, this just reduces to free s squared ds dt. So dv dt equals free times 12 squared times 0.6, which is the same as 6 over 10. That's free times 144. 6 over 10. And I'm sorry, I ran out of room, so I'm going to just have to write the answer here. Free times 144 times 6 over 10. I'll get both fraction and decimal point. But you'll be more biased for this answer in the AI course. And what is it? So that's centimeters cubed per second. Now we gotta get the dimensions to match that. Cube for cubic. Because you're multiplying three lengths together to get a volume. Alright. Alright, that's good and done. Think two more, and then we'll call it for today. Given that y equals free sine of, is it 2 pi x? It's 2 pi x. Y equals free sine 2 pi x, find rate of change when x equals 7 over 2. Well, since they specified the independent variable, and this function depends on x, it's going to be dy dx, or y prime in this case. And when x equals 7/12. So then dy dx. Okay, this is a composite function. And I get free sine of, free derivative of stuff of sine, which is cosine. So you get free cosine of 2 pi x, and then you multiply the inside of multiply by the derivative of 2 pi x on the inside, which is just going to be 2 pi. 3 times 2 pi, 6 pi, cosine 2 pi x. You want 7/12, so 6 pi, cosine 2 pi, 7 over 12. Here you would go and get your calculator. Make sure you are in radian. Make sure you are in radian. Otherwise the answer you get is going to be nonsense. And then get that 6 pi cosine of 14 pi over 12. I can do some quick simplification here. 2 times 7, 2 times 6, 7 pi over 6. So you then rotate by an angle of pi over 6, which I think is 30 degrees, 7 times, the bar of that. Cosine 7 pi over 6. I am in radian right now, I am in degrees. Okay. And they gave me a negative answer like this, which can only make me think that since it's dealing with a 30-60-90 triangle, that's going to be, yep, yeah. Actually no, let me do. If you get an irrational number for multiples of pi over 6 and pi over 3 or pi over 2, that means you get square root of 3 over 2. That's all this is. So let me just write this as a nice exact answer. 6 pi over 3 times negative square root of 3 over 2. You just have to trust me on this, please, and just follow it from there. 6 divided by 2, 3 pi, negative square root of 3, negative 3 square root of 3 pi. We are done. We are done. Actually, yeah, I guess we could like put this into 3 significant expressions because like we're the AI, we're biased with in the base 10 representation. Since that would make sense for the sciences or stuff, so that's approximately negative 16.3 units squared. Oh, sorry, units per. How do I do? Yeah, how do I just do? I have no idea what the units are. It's just like it's a slope of like a unit over unit, distance y over yeah. It's dimensionless. It's dimensionless. So units over units cancel. It's like this is y units and this is x units, but there's still going to be centimeters over centimeters. So these cancel out. It's dimensionless. So yeah, it's just a constant, negative 16.3. And we're done in that case. Okay, and the last one, this will take time because it's an optimization problem. Which basically means critical points apply to where problems. There's a cuboid, which means it's almost a cube, but not quite. So it's like a cube base, a square base, and then like it's projected by a variable height. So it's really a rectangular prism of a specific kind. You have a square base of side A and height H. So the base here is a square, but you project it up by a height that is not equal to that, and that value is H. The volume of the cuboid, so this volume of this, V equals 1,000? Is it 1,000? 1,000 cubic meters. V equals 1,000 cubic meters. Show that the surface area of the cube yeah, sorry, my handwriting is just going to be atrocious at this point. Surface area of the cube, of the cuboid, is let's see, and it's going to be a function in terms of A, so S of A, they write it as S, so they really should write it as a function of A, a little bit sloppy there in my opinion, to A squared plus 4,000 divided by A. So this is a surface area function, or SA. Surface area. And unfortunately for that, you just need geometry. You just need geometry. Okay, so let's see, do I have color on my side today? Yes, I have color on my side today. We will have 2 copies of the square base here. You're just counting it and then like doubling it together. Counting principle. So it's a squared plus a squared, or 2a squared in this case. So that checks out. So S of A equals 2a squared. Okay, now the problem is I could express this as, okay, sorry. So we have two square bases here. Next we have two rectangle edges here. Oh wow, this is a horrible mark. And I just went to go and buy new. We have two rectangular bases here which are opposite each other. And then, yes, unfortunately, if you have bad depth perception, your eyes are going to get screwed by this. Ow, 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 ow. Which is yet another 2 plus. God dang it. Which is then another 2AH. But then we have one more, which is like opposite here. And then here, I can't shade it, light is not good enough marker for that. And that is given by, yeah, this is 2AH again. So we get 2a squared plus 4AH. However, the surface area function is only done in terms of A. No, it's in terms of H. Where did they get this thing from? Well, what they had to do is they had to go manipulate a constraint equation. And what other equation could you have? Well, you can have the surface area of a cuboid, but you can also have its volume, which is this thing given over here. So like the volume of the cuboid equals length times width times height. And that's basically going to be A times H. So V equals A squared H. And then you just solve for H. So V over A squared equals H. Now you know that V equals 4,000. So H equals 1,000 A squared. Then you just plug in that H into here. So then S of A equals 2a squared plus 4a, 1,000 over a squared. This a and this a cancels here. You get 2a squared plus 4,000 over a. Yay, that's part 1 done. This is going to be a 3-part question. So this is part 1. We're done with part 1. Hooray. Now find the value of A for which the surface area derivative with respect to the length A is 0. Two A squared plus 4,000 over A, 2A squared plus 4,000 over A. So I want to find like ds over dA equals 0. And then find what value I get that for. So this is a quadratic, which is nice because then that means that the derivative function of this is going to be a linear function. So you get 4a, oh, I should have rewritten this. Because we don't like the a in the denominator, we want it to be in terms of fractional or negative exponents. So then this is 2a squared plus 4,000 a to the negative 1. That's S of A. Now we do ds dA. 4a, negative 1 down, decrement by 1, so that's minus 2, so that's minus 4,000. A to the minus 2. So that's 4a minus 4,000 a squared, and this equals 0, given that's the assumption that we were given. So then you could just move this to the other side, or actually no, it's better to, so you don't want to do any premature canceling. That's a problem that can happen, unfortunately. So we just multiply both sides of this equation by a squared. So we have 0 here. And then this is minus 4,000, and then this becomes 4a cubed. Is 4,000 a cube? If 4,000 is a cube, then we can do a difference of 2 cubes, but I am not optimistic about that. It is not. Okay. Well, you can do 4,000 divided by 4 and... Oh yeah, actually let's do this. We can factor out like a common factor out of there and disappear it by 0. So 0 equals 4 times a cubed minus 1,000. And so the 4 gets canceled, literally. A cubed minus 1,000. Oh yeah, that makes sense. 1,000 is not a cubic number. Oh wait, never mind. I don't have to worry about this. I was just saying that in principle, if you really want to go and like solve this carefully for values of a for all sides, if this were a random function, not constrained by a real life situation where your lengths a has to clearly be greater than 0, length must be positive. But if you did not, then what you would do is over here, once you open your TI-84, you go to y equals here, y graph, then you type in the function itself, which is x cubed minus 1,000, and then you graph the thing. Oh, sorry, I'm not doing a... And why is it not showing? Oh yeah, because the scale is horrendous. I have to go and bring y minimum all the way to minus, let's go with minus 1,500. Let's make y max, yeah, 5, and let's make the x min bigger, because those will probably be, I think, very large numbers. So negative 100, and then 100 here. Oh dang, okay, I can make it even more narrow. Negative 25, 25. Yay, see there? You got a nice picture like that. Oh wait, we wanted to look at where it crosses like the x-axis. So we want y max to be, let's go and put like a 25. Okay, it doesn't matter. Okay, because it's all the way there, and then the 25 just crosses here in this case. But that might not always work. You might get that like, because it's a cubic function in general can cross the x-axis 3 times, but in this case we're lucky. Just because of how it's manufactured. So then you plus 1,000 to both sides. 1,000 equals a cubed, and cube root both sides. Since this is AI and this is a word problem, you want to obviously represent this in a base 10 decimal notation. So let's just go and put in 1,000 to the 1/3, 1 divided by 3. That's 10. Oh, it is a perfect cube. Okay. I guess I didn't know. Okay, and then so a equals 10. That's the answer for part 2. And that's part 2. Done. And then the last part, and then I'm really tired of getting this out there. Show that this value of a gets the minimum value of the surface area, and find this minimum value. Show that this gives the minimum value. I have a feeling I'll need to go and find the second derivative function. Okay, so a equals 10. We have this function here, and a equals 10. I'm going to put this there. A equals 10. Okay, a little bit extra slow for like this part here. So the prompt says, show the value of A gives the minimum value of the surface area. Show A equals 10 gives minimum value of surface area. I'm just going to abbreviate it as SA. Find what that SA is. Yeah. Find that SA. I'm going to be lazy and do this first. So we just put S of 10. 2 10 squared. Oh yeah, since you're like AI, if you have like the TI Inspire or stuff, you could like end solve or like just put in like a number for that there. So then that's 4,000 divided by 10. So that's 200 plus 400 equals 600. Yeah, that's done. So that's the minimum surface area. It's 600 centimeters squared. Okay, but now, we have to show that this is the minimum value. Okay, so then we found, actually, yeah, I should get the derivative function again. Actually, no, we didn't differentiate this yet. Right? We didn't. I think I did. I erased all that hard work. Damn, what a waste. Now I have to redo everything again. Okay, fine. DSDA. That was so... Okay. 4,000 e to the negative 1. That's 4a. That's minus 4,000. A to the negative 2. And if we do this again, d squared s dA squared, that's 4. Minus 2 times 4,000 a to the minus 3. Let's see. So then we get 4 plus 2 times 4,000 a cubed here. So this is 4 plus 8,000 a negative cubed. And then if I put a is 10 there, and that's 4 plus 8,000 over 10 cubed. Which is 1,000, right? I'm not making this up, right? Yeah, that's 1,000. That's 1,000. 4 plus 8,000 divided by 1,000. So that's 4 plus 8, and that's 12. We don't care about the value of it insofar as this d squared as dA squared, which equals 12 at a equals 10, is positive. That means that you can classify it as a minimum. But the actual minimum surface area is 600 centimeters squared. Don't get them confused together. And we are done. Yeah, it's not even a proof. I'm not going to borrow the QED. Alright, that's it. Oh my gosh. Yeah, okay. Let me get the result. Sorry, yeah, stuff might have been cut off. I am not the best at camera work, and I'm looking at this video now, and well, it will be good for the audience, but right now looking at the review that everything is clear, everything is mirror imaged to the left for me. So I'm gonna have to figure out how to get this to work, but I hope that was useful, instructive. Please let me know any comments to improve, particularly on the practical part, with either using graphing calculator, showing working the graphing calculator, or just writing on the interface on the board. And I'll see what I could do. Other than I'll try to go and do this again in a TI inspired way, I swear. I'll just get the chance. Okay, thank you. Have a nice evening.